I'm concerned specifically about the exo-org cloud ejection calculation. Have you repeated that for Borisov? Because it seems like we'd run into the same issue of
I think, yeah, I run into the same
objects.
issue. Yes.
So maybe
yeah.
our assumptions about org clouds are wrong.
Because you say because this is clearly a comet. It's
right.
coming from.
And even let's assume it's different from Oumuamua, it still implies this number density.
It still implies a high number density,
yeah,
right?
Yeah. So maybe there's an issue with our assumptions about exo-org clouds.
Yeah. I mean the calculation will still be the same, right?
Right.
Because I will be comparing the numbers. So here. I will be comparing these numbers to whatever is here in Borisov. Instead of 2 times 10 to the 15, I will be comparing it to this range, right? 10 to the, it can be from 10 to the 14 to 10 to the 17. Yeah. So 10 to the 14 to 10 to the 17, I mean, even the lowest one will be still a factor of 10 higher. So yeah, there is still an issue there, yeah. So as I was saying, so there was the possibility of whether we could trap interstellar particles that are larger than a meter in these environments that are forming stars, and could we trap enough to make a difference? And what I do here is I look at different, so this was suggested last year by these authors here, and you can trap these particles, you could trap them in the molecular cloud stage, so really early on. You could trap them in the dense cores, in the kernels, like the ones that are being observed by ALMA, that are like 3,000 AU in size, or you could trap them in the main minimum mass solar nebula type of disk, right? So in this work here by Grisin, they look at the trapping of planetesimals in the protoplanetary disk itself. What I'm going to be concentrating here is at the efficiency of trapping in the molecular cloud environment and in the dense core environment, and so how many planetesimals could be trapped in this environment, and how many of those could get incorporated into the disks of the planetary systems that are being formed. And I do that, I don't know how I'm doing on time, okay, so I'll go through this quickly. So the way that you can trap is is either thanks to the gravitational potential or gas drag, right? If you look at gas drag, you can go through all the numbers, but maybe because of time, I can just give you the punchline here. So the acceleration due to gas drag will be depending on the gas drag, right? But let's go to the end here. So that will be, wait. Where am I? That. Here. So can you trap the particles with gas drag? Basically, the best thing that you can do is look at the momentum. So if you calculate what is the column density of the incoming interstellar objects, and you compare it to what's the column density that it will be swept by the gas, there are many orders of magnitude difference. So in the environments that I'm looking at, that are this type of environments here, for a molecular cloud and for a pre-stellar core kernel, the molecular cloud has like 10 to the 2 particles per centimeter cube. For the pre-stellar core, I'm assuming like 10 to the 6, and I'm assuming a molecular cloud that is like 30 AU 30 parsecs in size. And for the pre-stellar core kernel, I'm assuming it's 3,000 AU in size. And so for those type of environments, and for particles that are between 50 centimeters and 50 kilometers, what I find is that you cannot have enough column density in the gas, basically, in order to stop the particles that are coming in. And of course I need to assume some incoming velocity, right? And for the incoming velocity, I am assuming that it is a Gaussian distribution with a dispersion of 30 kilometers per second. And the reason why I am assuming this is because, well, the mean velocity dispersion of the molecular clouds in the galaxy is between 1 and 10 kilometers per second, and then the velocity distribution of young stars in the galaxy is, of course, is like a triaxial, right? But it has like one of the has a dispersion in R of 30 kilometers per second, and I'm assuming that the objects are coming from these stars in the galaxy, right? And so I'm assuming basically that they have a distribution. I'm going to assume a Gaussian distribution center at 0 and with a dispersion of 30 kilometers per second. And I'm assuming that there is center at 0, that is a Gaussian distribution center at 0, because in the solar neighborhood, we are near co-rotation, so there is basically no difference between the rotational velocity of the stars and the rotational velocity of the spiral arms, even if you assume that the star formation is taking place in the spiral arms, which is probably only the case for high mass, right, but not for low mass. Anyway, so that's the assumption that I am doing for the velocity distribution. So if you plug...
You're ignoring the possibility that there could be objects coming from the other side of the galaxy, because then you can get hundreds of kilometers per second.
Right, and for those it will be more difficult to trap them. Right, right. So I'm only looking at the ones that are coming from the neighborhood, the solar neighborhood. So in that case, you can assume that it's like no streaming velocity, basically. So assuming no, but even if you assume no streaming velocity, you can just not stop the particles. So gas drag doesn't help us at trapping planetesimals in these star-forming environments, in these early stages of the star-forming environments, which is like the molecular cloud or the prestellar core kernel. And then we can look at what is but we still have the gravitational potential, right? And so you can estimate what is the escape velocity for each one of these environments, and then basically you trap everything that comes in under that escape velocity, right? And this is, so basically you have an increase in the number density of planetesimals compared to what is in the background based on the number of particles that you can trap. That is basically, this is basically the tail of the Gaussian distribution that is under the escape velocity. And the escape velocity I calculated for the different environments. If you plug in the numbers, because I know I have to hurry up here, when you plug in the numbers, you get here. You get that just based on the gravitational potential, you get an increase on the number density of objects that will be in this environment just because you trap them due to the gravitational potential. You get the small increases with respect to the background distribution of objects. And you can estimate how many of these objects can get accreted to each one of the systems and how many will be remain. And so this will be the number of captured interstellar planetesimals per stellar system. And you can do it for the molecular cloud. And basically it's this number here. And it's going to depend on what is the background density of interstellar objects, right? And these are the numbers that I calculated before. What is the background density that you expect from like a protoplanetary disk origin, right? So how many objects do you expect to have uniformly distributed in the galaxy of these free floating objects? And using some different size distributions, you can estimate this number for different sizes. So basically, if I put here the estimates for how many objects you expect to have between 50 centimeters and 5 meters, and between 5 meters and 50 meters, and between 50 meters and 5 kilometers, then this is the number that you get here. So I can do that for the molecular cloud environment, and I can do that for the prestellar core kernel. And basically, this is what the numbers that I get. This is assuming, for simplicity, I'm going to assume just an equilibrium power law, so with a slope of 3.5. This is the total number of particles that I expect to have in each system to have been trapped from the interstellar medium per star. And this is, and I'm going to compare that to the results from Grissom et al. That estimate how many will be trapped in a protoplanetary disk environment. So what I'm doing here, I'm trapping them in the molecular cloud stage and in the prestellar core stage, and then they get incorporated into the individual disks. And I'm going to compare that to what this group expects to trap by each individual disk. So basically, what I get, these are the numbers in the 50 to 5 meter range. So these objects already would be able to overcome the meter size barrier. And you see that the numbers are pretty high. And you see that basically what you can incorporate at the early stages of star formation, of the star and planet formation, is comparable to what the number that you will expect to incorporate based on the trapping of those particles by the protoplanetary disk itself. So you can, the bottom line is that you can incorporate a large number of particles at all these stages, and that these scenarios that you can, and of course the number goes down as you increase the size of these particles, but we are more interested into these sizes, right, because that's when you have already overcome the meter size barrier. So the numbers are high, and of course, and the bottom line is that within these scenarios should be considered in future planet formation models, but also we need these models to tell us how many will be enough, because I don't know if this will be enough, right? I mean, we don't need to form that many planets, but I don't know how many seeds you will need to make a difference, right? And of course, this could not provide the first generation of seeds, because we are assuming that these seeds are coming from other systems that have already formed planets. But it can help. But as time goes by, the number of these objects ejected in the galaxy will increase. So as time goes by, this trapping might alleviate the need of requiring that all planet-forming disks have these very fine-tuned conditions in order to overcome these meter-size barriers. So, and then, of course, I was telling you that this assumes